Good morning. Welcome to Physics World. Today we discuss about a new chapter. Before telling the title of the chapter, let me introduce it. Every day in the morning we do so many things, like we walk, we run, we throw a ball, we catch a ball, we hold a book, we hold a pen, we stand. So like that we do so many varieties of things. But what is required to do all these things? Yes, it is energy. We require energy to do all those things. But energy is not the only thing is doing all the things. Energy is the source, but something else making us do all these activities, and that is none other than force. We cannot expect the world without force. If force is absent, I can say that our life is absent. No life exists anywhere. So force is the part of our life. If you hold a book, you are applying the force. You are pushing a table, you are applying the force. You are pulling a drawer, you are applying the force. You are walking, running, talking. Each and every situation, you are with force. Force is following you. That's why we need to know more about force. And more than that, we need to know that how to measure the force. In the previous chapter, motion, we discussed what is the speed, velocity, acceleration, etc. But how this type of motions are happening? It's only due to force. So that's why in this chapter we discuss about force and type and the different properties of the force, and we also learn how to calculate it, that is quantitative information about force. That's why today's chapter is force and laws of motion. On the board you are seeing some examples. The examples like pushing a trolley, pulling a drawer, compressing a spring, stretching a spring, seesaw. When you go to any park and playground, you can see the kids are playing the seesaw. They are applying the force. Twisting. So in all these cases we have force. And I am not saying that these are the only cases. We have some huge amount of cases. Some examples I gave to you. So let us move on to the actual concept of force. First start with balanced and unbalanced forces. So what is balanced force? Let me draw a diagram and explain you what it is. Take a block of mass m. On this block you are applying a force F1, pushing with the force F1. Now you are applying the same amount of force F2. I have given different label, but it is equal force applying on the other side. Say F1 has the value 1 Newton, F2 has the value 1 Newton. Even though both forces are magnitudely equal, but direction wise they are opposite. F1 is opposite to F2 or F2 is opposite to F1, but still their magnitudes are equal. Then we say that this block is balanced, and the forces are called balanced forces. And in this condition, the block is either resisted or it is in uniform motion. Because when these two forces are acting on the block, which are equal but opposite, but you take the total forces acting on the body, take minus F2 to the left hand side, F1 plus F2 is a total force which is equal to 0, and this is called net force. So net force acting on the body of the block is 0. Then F1 and F2 are called balanced forces. And this situation is called translational equilibrium. Translational equilibrium. That means it is the state where net force acting on the block is 0. And I told you already, in this situation, body is either at rest or in uniform motion. See this example here, it's a marker. Using my right hand, I am pulling the marker, so going towards right side. Using my left hand, I am pulling the marker, it's going towards left side of mine. But if I apply the force equal and opposite, now what's happening? It is a rest state. Still force is applied here. Don't think that I am not applying the force. Yes, I am applying the force, left side and right side, but still the body is at rest. Now I say this is in translational equilibrium. And F1, F2 are called balanced forces. So when the balanced forces are acting, net force is 0 and situation is translational equilibrium. Now see some practical examples here. A car is moving towards east. It is moving towards east because of engine force capital F. But there is a friction between the wheels of the car, between the tires of the car and the road. Whenever F, capital F equal to minus small f, then we can say the car is in uniform motion and capital F, small f are balanced forces. Now in this situation, a person with a parachute is falling towards the earth in the air. Generally, with using parachute, is falling towards the ground means is in the air, is falling in the air. This person has weight which is mg. Soon we discuss later how we got mg here. So weight of the body mg, because the weight of the body is falling down. But one situation, what happened, you know, this weight of the body is balanced by air friction. Air friction. Then you can say mg equals to minus f. The net force acting on the body is 0. And this f and mg are called balanced forces. And situation is translational equilibrium. See the third example, tug of war. This person A applying the force towards him. Say the force is Fa. The person B is also applying the force towards him. Say the force is Fb. If Fa is more, then the B person move towards left side. If Fb is more, the A person move towards right side. If both are equal, like this, then both the persons are in the same state. And Fa, Fb are called balanced forces, and it is in translational equilibrium. So in that way, we have many examples to understand balanced force. In balanced force, what happened? You cannot bring the change in the state of the body. If you want to bring the change in the state of the body, you need to apply unbalanced force. A car is at rest state, you want to move the car, then you need to apply the force which is different one, unbalanced one, then car moves. A car is in motion, you want to stop the car immediately, then apply unbalanced force. In the two situations, you are changing the state of the body, and it's only happened because of unbalanced force. So let us discuss about unbalanced force. This is also called resultant force. Resultant force situation or unbalanced force situation comes, you have many forces acting on the body, but net force is not 0. Net force has some non-zero value. Then it is called unbalanced force or resultant force. Let me explain you more in detail. See the first example. It's a small trolley. The force F1 of 2 newtons act towards east. F2 equal 3 newtons acts towards west. What is the unbalanced force here or resultant force here? So you can see here it is F1 2 newtons, F2 is 3 newtons. Then how to find resultant force? When the two forces are in opposite direction, you take the maximum force, subtract the minimum force from the maximum. So here the resultant force is F2 minus F1. 3 Newton minus 2 Newton, which is 1 Newton. Force is a vector quantity. So it has magnitude and direction. So which side the body moves? So it is 1 Newton towards west. So you need to say towards west. Okay, so that is how you are finding the resultant force or unbalanced force. Now see the second example. Now if you want to solve this numerical, pause the video, solve all the numericals and play it again and match with my answers. Now see the second one. If the two forces acting in the same direction, F1, F2, F3 is also in the same direction. So resultant force is here F1 plus F2 plus F3 because all three in the same directions. So 3 Newtons plus 1 Newton plus 4 Newton. So the answer is 8 Newton. Which side? Towards east. Now third one. F1, F3 in the same direction but F2 in the opposite direction. So therefore you take F1 plus F3 total 6 Newton plus 2 Newton, which is 8 Newtons towards east side, but 3 Newtons left side. So therefore this is 8 Newton minus 3 Newton, which is 5 Newtons towards east. If you see this, a little different. F1 is towards east side, F2 towards north side, and both forces are not parallel, both forces are not opposite, but they are perpendicular. How they are perpendicular? See here, if I extend these lines, you can see that both have the angle of 90 degrees. So both forces are perpendicular forces. Now how do you solve these numericals? When you have perpendicular forces, you need to depend on Pythagoras theorem. See here. So this is F2 and this is F1. Now the resultant force always will be here. This is resultant force. Resultant force R. And to find resultant force, R equal to root over F1 square plus F2 square. Pythagoras theorem. So if you apply here, F1 square is 4 square, F2 square is 3 square. So which is 16 plus 9, 25, root 25, and root 25 answer is 5. 5 Newton is the resultant force. And what is the direction? It is south east. So it is southeast. Good. Now see the fifth one. One more little difficult one. It is not perpendicular, but F2 force applied such that it make an angle 30 degrees with F1. How do we solve? For this you should know vectors, resolution of vectors. Resolve a vector along cos theta and sin theta. So here, as F2 is a vector, it resolves into two components. One is along F1 and other one is along vertical. And here it is cos 30, F2 cos 30 it is, and this is F2 sin 30. Like that, the force resolved into two components. Now, our interest is to find the velocity or the force, not velocity, force along horizontal. So in a horizontal, the total force, if you see, F2 cos 30 plus F1. Cos 30, you should know the value, but I will tell you here. Cos 30 is root 3 by 2, F2 is 2, 2 into root 3 by 2 plus F1 is 3. So 2 cancel, 3 plus root 3. Root 3 is 1.732 plus 3. So this is 4.732 newtons. See the last one. Again, a simpler problem you have got. A realistic problem. A car is moving with a force of 20 Newton because of engine, and it's suffering with a frictional force of 5 newtons. So what is the resultant force? And resultant force is F1 minus F. So 20 minus 5. This is 15 newtons, and it is towards east. This is how you need to solve the numericals to find the force quantitatively. We have understood how to find the force quantitatively. Let us discuss more about mechanical force. Here I mentioned mechanical force because there are varieties of forces: electric force, magnetic force, gravitational force, centripetal force, electrostatic force, electromagnetic force, nuclear force. Many are there. But here our interest is to know more about mechanical force. Mechanical force means which we are applying force mechanically. Basically, mechanical force is of 4 types: weight, friction, normal force, tension. Let me write here. The first one is weight. The symbol is W. The second one, sometimes weight is also expressed with 2 letters, weight, WT. Friction. The symbol is small f. Normal force. The symbol is N. Sometimes they use R also. It is also called normal reaction sometimes. Now, fourth one is tension. The symbol is capital T. So, these 4 are combinedly called as mechanical force. Let me tell you the weight. You know the weight of a body. Weight of a body is nothing but a gravitational force on the body due to earth. So, if you take a block like this of mass m on the ground, this block has weight, and this weight always acting towards the center of the earth, and the weight formula is mass into acceleration due to gravity. Weight Wt equal to m into g, mass into acceleration due to gravity, and you know g value is 10 meters per second square. Approximate to take 10, but original value is 9.8 meters per second square. So weight equal to mg. Now second, friction. Third, normal. Friction, normal, both are called as contact forces. Why they are called contact forces? Because they only exist when 2 bodies are in contact. If you show only single body, you cannot show the friction or cannot experience the friction of normal force. The 2 bodies should be in contact, like tires of that car touching the road. So, 2 contacting surfaces, tire and road surface. Yes. When you hit a ball with a bat, ball is moving in the air. Ball is one surface, air is other surface in contact. So, this type of contacts only you can experience friction and normal. Now, let me tell you briefly about what is friction. More we discuss later. Friction. Friction is the opposing force to the relative motion of the body. It is the opposing force to the relative motion of the body. Means friction makes the body to comes into motion. It makes the body to comes to rest also. Both the ways are possible. How? See, a block is at rest state, but if you apply the force on the block, exact sufficient force, the block is in motion. So, the block is in motion because you apply sufficient force, but after some time the block comes to stop. Why? Because there is a frictional force between the block and the surface. So here the friction makes the body to stop. Right? Now sometimes friction makes the body to be in motion. And the example is, suppose you are in the car and the engine is ignited. You put the key and ignition started. When the ignition has started, the wheels has to move. When the ignition started and accelerated, the wheels has to move. Wheels only move when there is a sufficient friction between the tire and the road surface. If the friction is not sufficient, instead of movement of wheel, they skid at the slip. So in that case, the friction supporting the car to move. Similarly, a person walking on the road, when you are walking on the road, when you are raising your right foot and putting on the road, and you are raising the left foot, it's nothing but actually you are pushing the road in the backward direction. You are pushing the road in backward direction, and so you are moving forward. And how it is possible to push the road in backward direction? Because the friction force between your feet and the road. So in this case, the frictional force makes you to move in the forward direction. So here it is in motion. So you're pushing the road in backward direction, and your friction making you to move in the forward direction. So like that, frictional force is opposing force to the relative motion. Relative motion means if you are in motion, it makes the body to comes to stop. If you are at rest, it makes the body to comes into motion. That's what called relative motion. Okay, and frictional force symbol is small f. Now coming to normal force, it is also contact force. I told you already. So normal force acts at a point of contact and vertically upward. How? See here in these examples only. Suppose there is a block on the surface. Now this is the point of contact. You have so many point of contacts, but one point of contact, if you take from the point of contact vertically up, the normal force acts. How do you say that at that point normal force acts? Let me tell you. This block has mass, and this mass acts downwards. Not mass, sorry, weight. Weight acts downwards because weight is the gravitational force I told you earlier. So this weight acting downward, because of weight, the block has to go into the ground, but it's not going. Why? Because there is an opposing force which is balancing the weight, and that opposing force is normal force from the point of contact. So in this case, the normal force N equals to mg. Now if you take one more example, a car having two wheels. In this case, you have 2 points of contact. One is here, one is here. So this is normal, this is normal, normal, normal. But weight acting downwards, mg. So in this case, n plus n, 2n equal to mg. So two normal forces are balancing the weight of the car so that it should go into the ground. So in that way, normal always act at the point of contact in vertically up direction. Last one, tension. How do you feel tension? Tension you can experience in ropes, strings, threads, etc. Suppose there is a wall. To the wall, a rope is fixed. Now you are pulling the string, in this direction. So force is towards you. When you pull the string doesn't break because there is an equal and opposite force developed to your force by the string, and that force is tension. So tension is experienced when you're working with the strings. It is always opposite to the applied force. So like that, we have 4 types of mechanical forces. Now we are going to in depth of the concept. We learned what is the force, what are types of forces, especially the mechanical force. But who was the first person in the world to tell us that force can be measured, force can be experienced. And the first person was Isaac Newton, a British physicist, mathematician, logician, astronomer. He has got so many roles. He was the first president of Royal Society. Those were the days. In his age, many fellows, many young scientists were the fans of Isaac Newton. Like today, how we are film stars we have, and we have many people are fans of different film stars. In that time also, in Newton's age also, there were people who are fan of Isaac Newton, and they were called as Newtonians. And these Newtonians, they worshipped Isaac Newton. And what are the principles, what are the formulas he taught, they spread all these principal formulas in the entire world. Isaac Newton wrote a special book. Today we call that book as a masterpiece in science, in scientific world. And that book name is Principia. One of the two masterpieces in the world. One is Principia it is. In this Principia, he explained everything about force, nature, and how the different forces we have, what is pressure, everything. So Isaac Newton also famous for two things. The primary one is law of gravitation. It's very, very famous. This law of gravitation applicable for massive bodies. There he explained about the attraction force between two bodies. That we discuss later. The second one, which is our main context here, is laws of motion. To understand more about motion, he framed three laws. Newton's first law, Newton's second law, Newton's third law. These laws are very famous. Till today, we are using these laws, and in the space also, we are using Newton laws with little modification suggested by Einstein. So, the laws of motion have three parts: first law, second law, and third law. Yeah. So, how do we know quantitatively the motion of a body? One day, a student of Archimedes raised stand and he asked, Mr. Archimedes, why if I throw a stone, the stone is flying in the air, falling on the ground and moved to some distance and stopped? Why the leaves are flying in the air and after some time they are stopped? Then Archimedes told that it is due to the nature of the body. It is the nature of the stone that it has to stop after some time. It is nature of the leaf, it has to fly and stop after some time. And this nature was presented by the God. That's why the objects are working in that way, behaving in that way. See the answer by the Archimedes. That was the age, the scientific knowledge not that much improved, advanced. They believed God and they taught everything related to God. Next, the Galileo age. Galileo was very interesting and very intelligent person, and has got a very inquiring mind. He wanted to know that the same thing, why the objects are in motion, why the object is flying or object is what you call moving on the ground and stops after some time. He did many experiments and he told that it is due to a property called inertia. Because of inertia, bodies are in motion, or because of inertia, bodies are at rest. So he framed the inertia. But that inertia, nobody can experience. Nobody can quantitatively express. Quantitatively means they can't calculate. Then the next age, Newton was the first person, for the first scientist. Actually, he quantitatively expressed and told that how this force can be measured. So he framed a law, and that law says a body tends to be in motion, or you can say uniform motion, tends to be in uniform motion or at rest, uniform motion or at rest, until and unless an external force acts on it. External force means unbalanced force. So a body tends to be in motion or rest. If the body is in state of rest, it is the rest state only. If the body is in motion, it will be in the motion only, until and unless you apply an external force act on it. When you apply external force, immediately changes state. So that's how he expressed the first law. And the strange thing is that before Newton, Galileo also had given the same statement, but only he excluded this thing. He said a body tends to be in uniform motion or rest. That's it. A body is in rest, it is in state of rest. A body is in motion, state of motion. That statement is given, and he said that statement is inertia. But Isaac Newton improvised the statement, and he told that until and unless an external force acts on the body. So this entire becomes a law which is called Newton's first law. So when we understand that Newton's first law statement is an improvised statement of inertia, we can say that Newton's first law is also called law of inertia. A body tends to be in a state of rest or motion until an external force acts on the body. The statement is in first law, but it's also improvised statement of inertia, so you can say it's a law of inertia. Now coming to inertia, what is inertia? So inertia is related to mass, and we can say mass is the measurement of inertia. This statement is important to remember. Mass is the measurement of inertia. Means more the mass, more the inertia. Lesser the mass, lesser the inertia. Let me take an example. A big rock, a small stone are there. A big rock in front of you, a small stone are there. You are the top of the mountain. So you want to push the big rock, you want to push the small stone. If you just give a little push to the small stone started sliding down, rolling down on the mountain. But if you push this, if you apply the same pushing force on the big rock, does it fall? No. Still you apply the force, still it is not falling, because it has more mass, it has more inertia, so it wants to be in a state of rest. That's why it is not moving. Suppose a car is moving very high speed, very high speed. This is in motion. Now suddenly car driver has seen something in front of the car, away from 100 meters away from his car, and he applied the brakes. Do you think immediately car stops? No. It goes to some distance, because inertia. Because of inertia, it wants to be in motion. That's why still it is in motion. After some time it comes to stop. And the stopping distance, when you apply the brakes, the stopping distance depends upon the mass. Car has more amount of mass. That's why it takes longer time. But if you see the same case of cycle, same 100 meters he has seen something, if you apply the brakes, immediately the cycle stops because of less mass, less inertia. Car more mass, more inertia. So like that, mass is the measurement of inertia. Inertia is again classified into two types. One is inertia of rest. The second one, inertia of motion. Inertia of rest, inertia of motion. What is inertia of rest? When body wants to be in the rest state, that is inertia of rest. See the example. There is a glass, on the glass is a cardboard. Above the cardboard is a coin. Many times I have done this experiment. If you pull the cardboard quickly, then what happens? Then stone also comes with you? No. Stone drops into the glass. Why? Because stone is in the rest state at this location and wants to be in the rest state. That's why when you pull the card quickly, because of inertia of rest, it is the same state. But here nothing is there, so it falls into the glass. Inertia of rest example. Okay. Now go to this one. Carpet having so many dusty particles, and you want to remove the dust particles. You take a big stick and hit on the carpet. Then you can see the dust particles rise up. Why? Inertia of rest. Because they want to be in the rest state, but when hitting the ground, it rises up. When you when you shake the tree, the fruits are falling from the tree. Why? Inertia of rest. They are in the rest state. They want to be in the rest state, but because of pushing, they are falling. Pushing and pulling, they are falling. So these are examples of inertia of rest. Inertia of rest. This is also inertia of rest. Coming to this fan, electrical fan. When you turn on the fan, switch on the fan blades are rotating, you're getting the air. And you want to stop the fan now. You switch it off. Do you see the blades are stopped immediately? No. Blades will still continue to move for some time because of inertia of motion. This is in motion, still wants to be in motion. So it is the example of inertia of motion. So like that we have many examples of rest and motion. Now we will discuss about a peculiar example of inertia of rest and motion. That is a person in a bus, a person standing in a bus. See, this bus is at rest state. Person is also rest state. Many times it happens to you also. You are standing in the bus, in the rest state, in the school bus, and bus driver suddenly stopped. Then what will happen to you? Will you be in the same standing position? No. You will fall backward. As soon as you start the bus, you fall backward. Why it is happening like that? Let me explain you. If you divide the person into two parts, lower part, and upper part. Lower part in contacting with the surface of the bus. So what are the bus state? The lower part of your body is also in the same state. If bus suddenly starts, your lower part suddenly starts and move forward, but upper part still in the same location. So that's why you feel backward pulling. This is happened because of inertia of rest. Inertia of rest. Now coming to here, this is another different behavior. You are in the bus, moving bus, and driver suddenly stopped. Then what happened? Many times you have observed us. We fall forward. We fall forward. This is because of inertia of motion. So same thing I can explain you. Lower part, upper part. Same explanation you can give. Lower part in contact with the body. So the lower part is also in motion. But as soon as the car stopped, the bus stopped, lower part of the body stopped, but upper part still is in motion. That's the upper part moves in forward direction. You feel you're falling forward. So this is example of inertia of motion. So here falling forward because of inertia of motion, it is falling backward because of inertia of rest. Let us discuss about Newton's second law. See on the board, two objects, a bullet and a block. Bullet has mass small m, block has mass capital M, and small m is very much lesser than capital M. Now, when you fire the bullet moves with very high speed, very high speed. The speed of the bullet is very high. Firing the bullet means applying the force. Because of applying the force, small bullet moves with very high speed. Coming to the block, big mass, you apply the same force, but it travels with a small velocity. So this was the observation by Isaac Newton. He understood that small masses moves with high speed, big masses low speed. Take your experience also. When you are on the signal point, red is showing, you are on the bike, and next to you there is a bus. Both are in the rest state. Means engines are on, but rest state, you're not moving. As soon as the red signal changes to green, when you rise up, who will go first? You on the bike or the bus? Obviously you, because your mass including with the bike is less, so you go with very high speed, whereas bus cannot go with high speed because of big mass, less velocity. So the observation with Isaac Newton, he confirmed that mass is inversely proportional to velocity. More the mass, lesser the velocity. So m is inversely proportional to v. If you take v to the left hand side, this mv equal to constant, and he put the name as p. P means momentum. So it is momentum. So therefore momentum p equal to mass into velocity. This was the first observation by Isaac Newton, momentum. So if we take the SI unit of momentum, mass is kg, velocity is meters per second. So it is kg meters per second. Okay, so how to define momentum? It is a product of mass and velocity. That's the momentum. Let us do a small numerical on the momentum. So I am doing an example numerical here. Suppose a ball of mass 2 kg has thrown with velocity 0.5 meters per second. Then what is its momentum? So it's a direct formula, P equal to mv, right? So mass is 2 kg and velocity is 0.5. So this is 1 kg meters per second. That's the momentum. So far we have learned about Newton's laws, Newton's first law, second law and third law. And we have understood that how do we apply these laws in solving problems and real life situations. Now I'm going to ask a question to you. Why the world the way it is? Why the world shouldn't be in a different way? Why we are how we are? Why the sun rising in the east? Why the sun is setting in the west? Why the earth is rotating about its own axis? And why it is revolving around the sun? So all these natural things we are observing every day. But if you ask the questions ourselves, then it is a very tricky question to us, and critical thinking is required here. But in physics, we have answers to all these questions. And the answer is conservation laws. What are conservation laws? Conservation means constant. So these laws tells you that there are some physical quantities remain constant. Because of they are constant, the world behaving the way it is. The natural things what you are seeing around us, because of the physical constants remains constant. So we need to say thanks to physicists to explain those natural things based on these conservative laws. So let me give you a small explanation about all these laws. Of course, all these laws are not required for us. We're going to discuss about only one law, but let me explain you briefly about all these laws. So first law, conservation of energy, means energy remains constant. So you learned that you maybe heard about that energy, mechanical energy mainly of two types, kinetic energy and potential energy. So when you are running on the road or walking on the road, the energy what you have is kinetic energy. When you throw a ball in the upward direction, the ball has potential energy at the highest point. So when you are in motion on a road, you have kinetic energy. When you are any object moving against the gravity, then it has potential energy. So kinetic energy, potential energy changes, but total energy always remains constant. Because the total energy remains constant, the body is behaving the way it is. So next one, conservation of momentum. Earlier class we discussed about what is momentum. Now here the momentum remains constant. Until unless an external force acting on the body, the momentum of the body stays same. And because of that only, you can observe an example. Let me tell you. In Diwali, you put Diwali bomb on a surface, and you lit the what you call the bomb. In a few seconds, the bomb blasted. After the blast, what happened to the fragments of the bomb? Will they, all these fragments, will they go in upward direction, straight, vertically up? No. We know that all these fragments spread around the bomb, all 360 degrees. So why the fragments are spreading around the bomb in 360 degrees? Why? The answer is conservation of momentum. Next, conservation of angular momentum. Conservation of angular momentum. Here also angular momentum remains constant when no external torque acts on the body. It is applicable in rotatory motion. Conservation of charge means total charge remains constant. You can show high charge somewhere, you can show low charge somewhere, you can show positive charge, you can show negative charge, but total charge always remains constant. So we can discuss more about this conservative laws, but I told you that in our class we are not discussing all this. Those are not in your portion. So we have only conservation of momentum. So we discuss more about conservation of momentum. So yeah, one more thing. You may wonder that why I have left conservation of mass. I need to explain you. Conservation of mass. Maybe you learned or heard in chemistry classes. The mass of the reactants in a chemical reaction is equal to mass of the products. Hydrogen plus oxygen gives rise to water, H2O. H2 plus O2 gives rise to H2O. So how much amount of hydrogen and oxygen you have taken before the reaction, after the reaction maybe you get a new chemical compound, the total mass remains constant. That you have learnt in chemistry classes. So mass remains constant is what called conservation of mass. But later it was disproved by Einstein, saying that the total mass not remains constant. After the reaction, some mass is changed in the form of energy called binding energy, which is the famous law we can say, and the famous formula. You may heard that E equals to mc square, mass energy equivalent. So once this formula was introduced by Einstein, the conservation of mass is replaced by E equal to mc square. But this formula is more applicable in nuclear reactions. So as I told you, we are coming back to the conservation of momentum. So conservation of momentum says total momentum remains constant unless an external force acts on the body. That means when F equal to 0, an external force not act on the body, force is not acting, implies momentum P equal to constant. This is what conservation of momentum. How it is possible? Let me derive the formula. F formula according to Newton's second law, you know F is ma ma equal to 0. This ma can also be written as delta p by delta t, we learned in the earlier class, equals to 0. Implies delta p equal to 0, because delta t goes to right hand side, multiplied by 0, it becomes 0. And you know that delta p is nothing but change in momentum, which is p2 minus p1, final momentum minus initial momentum, which is equals to 0. Then implies you can write p2 equals to p1. That means final momentum equals to initial momentum. Whatever the initial momentum you have, the final velocity has the same momentum. That means momentum is not changing. That is, momentum is constant, and it's only possible when there is no external force acts on the body. This is what called conservation of momentum. So one more time, when no external force acts on the body, then the momentum remains constant, which is called conservation of momentum. So if you see the statements on the board, when no external force acts on a body, then its momentum remains constant. F equal to 0 m plus p equal to constant. This is the main statement of conservation of momentum. But conservation of momentum is very popular in the case called collisions. What is meant by collision? Collision is nothing but a body is coming and hitting another body. Like a car on the road moving and hit another car, or the bike hits another car, or two balls rolling on a board and hitting with each other. Or the best example I can tell you, when you play caroms, when you hit the striker goes and hit a coin, or maybe in the play one coin hits another coin. So this is what called collision. So in this collision also conservation of momentum is applicable, and it has a formula also. So let me derive for you that conservation of momentum formula in collisions. See this diagram carefully. There are two bodies of masses m1, m2. Let us imagine two marbles having initial velocities u1, u2. They collide with each other, and after the collision they move in the same direction with the different velocities v1, v2. We say final velocities. Now while they are colliding, see carefully, m1 mass applies force F12 on m2. Similarly, m2 mass applies force F21 on m1. These two forces are equal and opposite. F12 is equals to F21 and opposite. So do you remember anything? Do you recalling any concept what we learned earlier? Yes, this is nothing but action reaction forces, Newton's third law. If I say F12 is action, F21 is reaction. Action reaction both are equal and opposite. Okay, now let me write the expression for F12. F12 is the force by mass m1 on m2. So when this force applied on mass m2, according to Newton's second law, the force formula is F12 equal to mass into acceleration. But it's the mass on m2, so m2 mass into a. So therefore I will write m2 into acceleration. Which body gets acceleration? The body m2 gets acceleration. So the body's m2's acceleration is change in velocity by time. Change in velocity means final velocity minus initial velocity. m2 final velocity is v2, initial velocity is u2. So therefore I will write v2 minus u2 by time t. Now let me write F21, force by mass m2 on m1. Same, mass into acceleration, but this is on body mass m1, so m1 into a. So m1 into m1's acceleration. So m1's v1, u1. So v1 minus u1 divided by t. Okay, so these are two expressions. These two expressions now supplied here. So implies in this expression. So I am rewriting m2 into v2 minus u2 by t equals to minus m1 into v1 minus u1 divided by t. See carefully. T is nothing but time of collision. Now here, as the time of collision same for m1 m2 mass because they are simultaneous hit with each other. So tt is cancelled. So what you get, m2 v2 minus m2 u2 equals to minus m1 v1 plus m1 u1. Just check once. Minus into minus, which is plus. We got an expression. Now what I do? See what I am doing. Minus m1 u1 bringing to left hand side. So m1 v1 plus m2 v2 equals to minus m2 u2 brings to right hand side. So then we'll get m1 u1 plus m2 u2. Rewriting the same statement here. First I write this one, m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. So what is m into u? Mass into velocity is nothing but momentum. This is the momentum of first body p1, m1 u1. See, first body m1 u1. So p1 plus m2 u2, momentum of the second body p2, but these are the initial one, equals to m1 v1. This is the momentum of the first body, but after collision. So when I say after collision, I will write a p1f, means final, plus p2f. So what we understood with this, p1 plus p2i means this is the total momentum before collision. This is the total momentum after collision. So hence, the conservation of momentum can also be stated as the total momentum before collision is equals to total momentum after collision. And this is the very, very important formula for you for solving numericals. You can see the two statements of conservation of momentum. The first one already we discussed. The second one more time. Total momentum before collision equals to total momentum after collision. m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. So the second statement is very much helpful for you to solve problems in collisions case.